integration can be used to find the areas that are bounded by an algebraic function, the reference axis, the y and the x-axis, or any other graph that you may have on a Cartesian plane. There are steps to follow, and these are the steps. The first thing that you have to do is to sketch the function accurately on a Cartesian plane. Then you identify the required area, and you after that you choose what we call a differential element, or a strip, an infinitesimally small strip that you can choose. And then after that, you deduce a function in one variable and integrate it. When I say you deduce a function in one variable, I mean if you are going to integrate with respect to x, you need to deduce a function that is in terms of x only. Or if you are going to integrate in terms of y, you make sure you deduce a function that is in terms of y only. I'm going to illustrate this with an example. I'll show you the steps that you have to follow. Let us say we are given this question. Find the area bounded by y is equals to 2x, the x-axis, and x equals to 3. So we have three boundaries here. Three boundaries. Boundary 1 is our function y equals to 2x. So this is the first boundary. The x-axis is part of the boundary, and x equals to 3 is part of the boundary 2. Now we have now to sketch this. This is the first step, as I said. You sketch this on a Cartesian plane. Let me do the sketching. So let us say this is my y-axis and this is my x-axis, and from here I can sketch this line y equals to 2x. This is the line passing through the origin, and it is the positive gradient. I'm going to sketch that line. So the line will be like this. That is the line y equals to 2x. I'm going to call this line y equals to 2x. So it's y equals to 2x. That is the line. Now, it is part of the boundary. So y equals to 2x is the boundary. Then the x-axis, this axis here, is part of the boundary. And then we need another boundary. The third boundary is the line x equals to 3. So this is a vertical line. I come here, I call this place here 3. And we have a line here, a vertical line. This is the line that we call x equals to 3. Now, the area that is required, this is the area required. It is very important that you identify your area correctly. This is step number 2. Step number 1, you sketch the graphs, which is what we did, and then we have to identify the area that is required. It is a very, very important aspect of this process. Now we know the area that is required. Now from here, I want to do this in a different way. First, I think you can all agree with me that what we have here, this area is actually a triangle, a right angled triangle. If I put something here, this becomes a right angled triangle, and the height, this side here is actually a perpendicular height. So we can actually find the area of this triangle using ordinary trigonometry, or using the formula for finding the area of a triangle. I can find this area. I know that if this is y equal to 2x, at this point here, at this point, x is 3, and y will be 6. So x is 3, y is 6. This is this point here. So this is 6. So the height of this is actually 6 units, and the base is 3 units. I can find this area using the formula A is equals to half times the base, which is 3, times our perpendicular height, which is 6. From here, we can calculate the area, this bounded area as we want. So this will be 9 square units. So this is 9 units squared. We already know this. We already know the areas, but I'm going to use integration. So please follow the step that I'm going to take, because it doesn't matter what kind of function or what kind of graph that you're given. The process remains the same. The process remains the same. So pay close attention to what I'm doing here. I know my answer is going to be 9 units squared. I'm fine with that, but I want to show you how you do it using integration, so that if you're not having a definite shape like this is a triangle, and we have formulas for finding the area of a triangle, but life is not always linear like this. Sometimes we have a function that is not a straight line, and we still want to find the area of that function. We don't have the formula for it, but we can do it using integration. This is what I mean. All right, so now from here, let us approach this using the integration that I just mentioned. All right, this is what we have. Now we know our area. Let us choose what we call a differential element. A differential element of area. This is a small representation of an area in this big area. What we do here, we draw what we call a strip, a thin strip. You can use a horizontal strip, you can use a vertical strip. If I use a vertical strip here, it should be a very thin strip. It should be a very thin strip. So this is how the strip would look like. Very thin. All right. Obviously what I'm drawing is a sketch, but this is what happens if you draw a thin strip, an infinitesimally thin strip. This strip will have a thickness called dx, delta x. It's a small thickness called a delta x. It has a height, this height here, which is a y value. So the height is y. Just like on our triangle, we said this height here is 6, which is the y value. So we can just give it generally that, oh, the strip has got a height called y. And this strip, if these two lines are so close to each other, the strip becomes a rectangle. Very, very important to notice this. The differential element here is actually a rectangle. In other words, if we put these two lines close to each other, the curvature or the slanting of this line actually becomes unimportant. So we can actually ignore that there is curvature or there is slanting here. Then we can say this is a thin strip, which is a rectangle. So dA, the area of this small strip, dA is equals to y times dx. This is the area of this small strip. It is a rectangle, so the length of the rectangle is y, the breadth of the rectangle is dx. If we multiply y and dx, we get dA, the area of that strip. Now, this was the reasoning that Isaac Newton used. He said our whole area here is comprised of these small strips. There are so many, there are many of them. Which means if we add this small strip, we actually get the whole area. That's why here we put summation. We are summing, or we are adding. This integration symbol is actually saying summation. It's like an elongated S. There is summation here. So Isaac Newton said if we add these small areas together, we get the whole area. So we are actually adding, so we are summing from where? From x equals to 0, because we want all these vertical strips from this point here, x equals to 0, to this point here where x equals to 3. So we are summing from 0 to 3. From 0 to 3. It means from here, if we add these small areas from 0 to 3, we actually get A. The area that we're looking for, it is actually the summation, from 0 to 3 of y dx. I want to highlight something when you're doing this integration, when you're applying integration in all these applications. Please note that if you are integrating with respect to x here, dx, your limits of integration should be x values. I'm going to do the same question using a horizontal strip. And you're going to see that you get the same answer, but the approach is a little bit different. Now, if we are integrating from 0 to with respect to x, I said the limit of integration should also be x values. That's very important. And now we have y here, yet we are integrating with respect to x. We have to change and we have to generate a function in terms of x so that we can integrate in terms of x. This is part of the steps. Let me go back to the steps so that you understand where we are. Now we are here. We did the sketch. We did our sketch. We identified the required area. We chose our differential element, the strip. We did that. Then we deduced. We have now to deduce a function in one variable. So in this case, the function should be in terms of x so that we can integrate it in terms of x. Simple, right? Straightforward, right? Yes, this is what we have to do. Now, let's come back here. We know from here that y, we know from here that y is equal to 2x. So where we have y here, we can put x, such that our area is actually the integration from 0 to 3 of 2x dx. If we do this, then we are done. That is the last step. So you find a function in terms of one variable and you integrate it. So we can move on now to find our area. Let us do that. Let's find our area. We know the area, by the way, that it should be 9 units squared. So let us go there and find our area. Now we know that a here is equal to the integration from 0 to 3 of 2x dx. If we integrate here, we get 2x squared over 2 from 0 to 3. This is definite integration. We are doing definite integration here. I think you can agree with me that these ones cancel. So we are essentially dealing with x squared from 0 to 3. So we substitute our upper integration limit, which is 3 squared, subtract our lower integration limit, which is 0 squared. We get here 9 units squared. Just like before. This is how you do it. It doesn't matter whether it's a curve or whether it's what. All you have to do is to follow this approach to find the area. Now I want to go back and do the same question using a horizontal strip. So let me come out of here. I'm coming back here. I'm going to take out this, or let me just wrap the whole area and do another sketch. So let me put this off. Let me come here. I'm going to now use a horizontal strip on the same area. Now let us do that. Yes. I'm going to draw this horizontal strip. So this is our horizontal strip. It's a very thin strip. Very thin. Please don't rely on mine. It's a sketch, but in reality, we are dealing with a very thin strip. This thin strip has got a thickness. It has a thickness here, which is dy. I think you can agree with me. The thickness here is dy, small y. And the length of this strip from here to there is actually 3 minus something here. You see? 3 minus something here. 3 minus an x, because it's actually an x something. So it's 3 minus x. This is the length of this. It's 3 because the boundary here is 3. So it's actually 3 minus x. That is the length of this strip. Please get it right, because if you cannot deduce your differential element correctly, you will not get the right answer. Very, very key there. This is 3 minus x. I just want to give you an example. Let's say we are here. The length of this will be 3 minus the value of x here, which is 0. So it will be 3 units. I think you all can see that. That is this. Now, it means dA, our small area, dA, let me use this part here. dA, it means dA, our small area, is a rectangle by the way, will be 3 minus x times dy. 3 minus x dy. This will be our differential element, 3 minus x dy. If we add these, so we are adding these horizontal strips from this point here where y is equals to 0 to this point here where y is equal to 6, because these are they're stacked on top of each other, so we are adding them. That is why we say our area now, this dA here, we can put the integration sign here. Let me put it here. We put the integration sign here. If we add these areas from y is equal to 0 to y is equal to 6, from y equals to 0 to y equal to 6, if we add these areas, we actually get the whole area, which is a. It will be the integration from 0 to 6 of 3 minus x dy. Very, very important. Now I have deduced my area integral. Now look at this. I want to repeat it again. If you are integrating with respect to y, dy here, your limits of integration should be y values. Your limits of integration should be y values. That's why I'm using 0 here, the value of y here, to the value of y here, which is a 6. Now, let us move on. Now, we now know that our area is equals to integration from 0 to 6. 3 minus x dy. I said you cannot integrate in terms of y when you have an x here, which means you have to replace the x here by a function of y. What are we going to rely on? We're going to rely on this, our original function. From there, we can make x subject of the formula. From here, we can see that x is equals to is equals to y over 2. That is our x. So when there's x here, we can put y over 2, which means our area is essentially integration of 3 minus y over 2 dy. Awesome. Now we have done the last step, which is this step. Let me go back here and show you the step that I'm talking about. We are now here where we deduce a function that we can integrate in one variable. Now we have something that we can integrate, which is only in terms of y. So let us do that. So I'm going to come out of here and I'm here. Now we are going to integrate. So our area is equal to the integration from 0 to 6 of 3 minus y over 2 dy. Yes, we are able to integrate this. This means 3y minus y squared over 4 from 0 to 6. So now we're just going to substitute our limits of integration. We start with the upper limit. So this is like 3 times 6 minus 6 squared over 4. All of this minus 3 by 0 minus 0 squared over 4. This is how you do definite integration. You substitute your upper limit, then you minus and you substitute your lower limit. If you punch this in your calculator, this is like 3 times 6, which is 18, minus 36 over 4, which is like 9. So if you punch this in your calculator, you get 9 units squared, which means you get the same answer as before, but we used a different approach. I hope this is very clear for everyone. I am just doing an introduction here. This is how you do the calculation of areas given function. It really doesn't matter the nature of the function, however it looks, it doesn't matter really. The approach remains the same. I'm going to do another video where I explain this approach when we have graphs that are not linear, and also the area being enclosed by two graphs. But before I leave this, I just want to give you some heads up on something. Now let us say your area that you're sketching, the importance of the sketch. Let me say the sketch here. And why the sketch is important. If you sketch your Cartesian plane like this, and then on the Cartesian plane, you have, so this is you have your x here, and this is your y. If let us say you're looking for an area like this, the area is coming like this, and you are required to find the area enclosed by this function from this point here to this point here. Yes, from this point here, let's call this point A, we have this point B, and we have another point called C on this, and this is our y equals f of x. And you are required to find the area enclosed by this function and the x-axis, which if you do the sketch, it is this area here. Please guys, if you have done your sketch and you see that the areas are like this, do them separately. In other words, find your A like this, because this is the reasoning behind it. This area here is negative. The area here on top here is positive because it is above the x-axis. If you integrate directly from here from A to C, if you integrate directly from A to C, in other words, if you integrate f of x dx from A to C, you're going to find 0. The area is going to be 0. Why? Because you're adding a negative number here and a positive number. If you add them, you get a 0. That is what integration is doing. So if you make a sketch and you see your areas like this, put them separately or integrate them separately, such that our A in this case will be equals to integration of f of x dx from A to B, and then plus, use a minus here. Use a minus. I'm putting this minus here because from B to C of f of x dx, I am putting a minus sign here before this integral because I know what I get here should be negative. So I'm multiplying it by negative already so that we can have addition. Or you can just do the integration separately and add the areas, ignoring the negative signs. Remember, area is not a vector, it is a scalar, which means it shouldn't have a sign. You don't have to say minus 2 square meters, you don't have to. The negative sign there is just telling you that it is below the x-axis. It's a negative area because it is below the x-axis. It is telling you that. This is the importance of doing the sketch, so that when you're doing your integration, you know exactly what to do. If you just do it blindly, you may not get the right answer, because these negative areas and positive areas, if you add them, they will not give you the correct area. There will be subtraction of some sort that happens there. Please pay attention to that. I'm going to illustrate this with other examples. Otherwise, thank you for watching the video. If you have any comments and queries, just write in the comment section below. Give the video a thumbs up and subscribe to the channel.